everyone. Welcome to the fifth and last spring lecture of this year. Today we'll have a master student from the L.A.D Observatory, Saphira Brandenberger, give a talk about ocean worlds beyond Earth and could they potentially harbor conditions that would be able to support life. Saphira got her bachelor's degree in Vienna and started a master's degree here in Leiden almost 2 years ago. Now she's in her second year. During the 2 years, as a standard for any master's student of astronomy in Leiden, she completed 2 research projects under supervision of professors here in Leiden. So her first project was with Nienke van der Maren, and it was on formation of ultra-short period planets, which is about to be published in a prestigious astronomical journal, actually. And her second project, which she'll be talking about today, is the habitability of exoplanets, which is being supervised by Professor Shamina Miguel. So take it away.
Okay. Yeah, I think the microphone's working. Perfect. So hi, welcome everyone. Thank you so much for coming today. My topic today will be habitability. Again, my name is Saphira, and I'm a second year master's student. And yeah, this is a big topic, is ocean worlds beyond Earth. Could they be habitable? So we're going to go a little bit beyond the topic of basic habitability and look into more exotic habitability. First, let me ask you a task that you can do. So try to imagine a habitable planet, some planet that could potentially host life. Try to visually imagine it in front of your eyes for a second. So I think that most people probably imagine something like Earth, because let's be honest, the only good example of a planet that hosts life is Earth. We don't know of any other planets, so this is the basic example we take when we are searching for other planets that could host life, potentially. But in recent years, we have discovered a lot of exoplanets, so planets outside of our solar system. This is just a graph that is showing us the counts versus the discovery year. So we can see that there are some peaks. This is when big missions were being launched and we discovered a bunch of new exoplanets. At the moment, we have discovered about 6,000 exoplanets, so quite a lot of exoplanets that we have now discovered. And funny enough, a lot of them look like nothing that we have in our solar system, so we have no equivalent of what we are finding out there. And this raises the question, is Earth like the only kind of habitability out there, or are there other possibilities? So I will take you through these topics today. First, I will start with some basics. We'll start from the solar system, then we will go into the topic of habitability and how we detect exoplanets generally. And then we'll go beyond the solar system. What kinds of planets are out there, and could any of them be habitable? And lastly, I will talk about my current master project that I'm doing, show you the problem that I'm trying to tackle, and my proposed solution. So let's start with the solar system. This is a wonderful artist's impression. We can see our 4 rocky planets, more commonly Earth, Mars. And we can see the larger outer planets, Jupiter, Saturn, Uranus, and Neptune. This, however, is an artist's impression. It's just meant to be beautiful in the end. And there are 2 things that are quite off. The first thing are the distances. That would not work, how it is drawn right now, so close to each other. But the second thing that is also very off are the scales. So this image is not true to scale, considering the sizes between the planets. Because the sizes of our solar system objects are very, very different. We are seeing the 4 inner rocky planets, so Earth, Mars, Venus, and Mercury, are tiny in comparison to our gas giants, Jupiter and Saturn, and our ice giants, Uranus and Neptune. I always find it most impressive to look at the comparison of Earth versus this spot. This is a storm on Jupiter that has been going on for, we think, 180 years, because that's the first time we are kind of writing it down that there's a spot. And when we're looking at the comparison of this storm that's happening here on Earth can fit into that spot, into that storm, about 1.5 times. So I always find it very interesting to see that we have such very different scales between planets. What is also different is their interior. So different sizes, there come different planetary interiors. For the rocky planets, we have more of a rocky composition. That's why we call them rocky planets. We're having elements like iron and silicates, and we have a solid crust. And then we are going to the gas giants, the much larger ones. They're mainly composed out of more lighter elements like hydrogen and helium. And then we have the ice giants, Neptune moons. Those are made out of ices like methane and water. And when we look at Earth, we see a very special planet. We see it is small, so it's rocky. It has oceans, which is quite rare. It has a lot of liquid water. And it has a very thin atmosphere, which makes it possible for the liquid water to stay liquid. Actually, in general, when we're looking at Earth, we see life everywhere. No matter where we look, we see animals, we see each other, we're all life in the end. We also see forests, and we have a great diversity of life on Earth. So of course, we're taking it as our home. Makes sense. When we're looking at a habitable planet, there is like this common sense in astronomy that a habitable planet probably needs just one thing that we're basing our definitions off. Does someone want to make a guess what this one thing is that we're kind of basing the definitions of a habitable planet on?
Water.
Yeah, water, yeah, super easy. It's water, but specifically in its liquid form. It has to be liquid. Does anyone know why specifically liquid water? Why is it so important?
It's the medium for all kind of chemical processes.
Amazing, perfect answer, yes. Exactly, so it is the solvent where our chemical reactions that facilitate life are happening inside. So the chemical reactions need a medium, and for all life that we know, it is liquid water where those reactions are happening inside. And to maintain this liquid water, as I said, we need an atmosphere, we think. There are other possibilities. We have come up with other ideas of how liquid water can stay on the planet. For example, underneath an ice crust, if we have some heat coming from the inside of the planet, we're thinking there could be liquid water. For example, we had this discussion on Europa, and this is a moon of Jupiter in our solar system. But generally, when we're thinking of habitable planets out there, we are thinking of it should have liquid water and an atmosphere that makes it liquid. And this is where our definition of the habitable zone comes in. The habitable zone is the region around a star where water on the surface of this planet could be liquid and invincible. So this definition is quite based on Earth-like planets. So it was first calculated based on an Earth-like atmosphere and Earth-like conditions, and we're just looking at, okay, at what distance does it stay liquid? But because if we're going too far inside, the water is evaporating, it's not liquid anymore. And if we're going too far out, it's going to freeze out. And we want it liquid because we need a medium to be liquid. It's also often called the Goldilocks zone because of Goldilocks. She wants it not too hot and not too cold. So this is the definition of the habitable zone. But how do we even detect planets in the first place? That is the big question. So the most common or most popular technique at the moment is the transit method, where we are pointing our telescope towards a star, and we are observing the brightness. And we can see it here in this animation. Once something goes in front of that source, the light is dropping. Quite simple. If you're looking at a lamp and you're holding your finger in front of it, you will see that there's less light coming in if there's something in front of it. And this is the whole theory behind the transit method. We're just looking at the star, and once the planet goes in front of it, you're observing the light, boom, we're having a dip. And this dip is different for different planet sizes. If we're having a larger planet in comparison to the star, we get a larger dip. Here we get a smaller dip. So this transit method also works quite a bit better if we're having larger planets in comparison to the star. What we can also do here, and this is quite important for research for life elsewhere, is we can take a so-called transmission spectrum, which just means if the planet has an atmosphere, you can see here a little bit of a, sorry for that, you can see here it has an atmosphere, and when light passes through the atmosphere and you're having certain molecules in there, they're absorbing the light at different wavelengths. And when you're looking at the light, so this would be light normally, you're having just this spectrum. When you're looking, you're having these dips. And these DIDs are molecules observing at different wavelengths. So you can have methane, water. This is just, in theory, this is not data. This is just to have a nice visualization. And this is what we call a transmission spectrum that tells us what could be in the atmosphere of that planet. And this is very important because those are fingerprints. And we can understand what this atmosphere could be made out of. And for different planets, we then get different spectra. Those are just examples from Mars, Earth, and Venus, from the solar system. We see that all of them, all three, have a dip in carbon dioxide, but only Earth has a dip in ozone and water. And that is hinting towards the next topic, biosignatures. Biosignatures are possible signs of life, we say, because when we're looking at Earth's atmosphere, we see certain molecules that we think can only be there if life is restored in them. What is important here is the combination of those molecules. Just because we find methane, if you find methane in the atmosphere, it doesn't really mean that this is really life. Only if you're seeing certain combinations, you're like, okay, how else could it be restored if it's not because of life? If you're seeing, for example, oxygen and methane together, they would, after some time, we say, not destroy each other, but they would turn into other molecules, they would react. And if you're finding both together, it means that methane and oxygen are being both made at the same time, or replenished into the atmosphere, by processes of life, we say. So yeah, that's why we're searching out there for so-called biosignatures in the atmospheres of exoplanets. And this brings me to, where should we look first? Where should we go to look for these habitable planets? Well, the first guess would be the habitable zone, because we say, okay, in the habitable zone, we could probably have liquid water. So what we are looking for right now is a lot for rocky planets, so the smaller ones, inside of this zone where we could potentially have liquid water. We've also found some of these planets. We have, for example, very well known as the TRAPPIST-1 system, because we have this guy here, this planet here, called TRAPPIST-1e. We're just naming planets with letters because it works well. So this is the first one detected, being B, C, D, E, F. So this one here, TRAPPIST-E, is often highlighted as the best Earth-sized case, and it's also inside of the habitable zone. And this doesn't mean that it has life. It just means, considering it's in the habitable zone and it's approximately Earth-sized, if there is water, it could be in a liquid form, but that is essentially wrong. And another example is Proxima Centauri E, because it's very close to us, it's the closest outer solar system to us, and it is Earth-sized. So we're saying, wow, this is great, it's an Earth-sized planet, and it's also in the habitable zone. But now comes the turning point. We have been observing a lot out there. We saw those peaks in the beginning of the slide, where we saw that we detected a ton of planets over the last years, specifically with Kepler and TESS. And what they found out is that the most common type of exoplanet out there is probably not Earth-sized planets. It is probably something called Sub-Neptunes, mini-Neptunes, super-Earths. And now it really depends on who you're talking to in the field if they're going to call it a Sub-Neptune or a super-Earth. But generally, those are planets that are in size between Earth and Neptune. So when we're taking again from the star, the size comparison between Earth and Neptune, Neptune is about 4 Earth radii, so 4 times the Earth essentially. And we're finding a lot of objects that are in between in size. So we have no analog in the solar system because we only have this size and then we have this size and nothing in between. So we are wondering what it could look like. Those are again artists' impressions of these type of planets that we found. So we found one that is quite a bit larger, we found one here, we found a lot of them, and we're just wondering what could it look like inside, because we cannot figure out the composition from so far away. They may have different atmospheres, interiors, surface conditions. It's an open question. What researchers also found is that when you're drawing, or when you put it, so we are having a number of planets per star, so how many we have per star, and their size, so their radii. When we're putting them on a graph, we see 2 peaks. Meaning that for in between 1 and about 1.8 times the Earth, we're calling them super-Earths. We're having a peak, so we're having more of them. Then there's a dip. All of a sudden, there are a lot less. We're finding much less. And then we're having a peak again. So in between 1.8 and 4, so up to Neptune, we're finding again a lot of these planets. And yeah, researchers have now come, not all of them do that, but a lot of them call this peak here the super-Earths, and then this peak here is the Sub-Neptunes. And in between, we call it the radius valley, because it's a valley when you're drawing the radius on the x-axis. And what we're thinking is, because when you're calculating the density of a planet, it is proportional to mass over the radius, that these here should have a higher density probably, and these here should have a lower density probably. So these different, we now call them populations, could have different interiors, we're thinking. These would make more sense to be more like the rocky planets that we have. And this here, this is the big question. Because when we're looking at the density, for the density combination, we could have, well, a lot of rock and then some hydrogen and helium, so lighter elements. We could also have rock and then a layer of water, or the mixture. It all works for the same densities, for the same mass and radius combination. And this is a big question for the Sub-Neptunes. So, about the larger ones, the Sub-Neptunes. There are these different possibilities for their interiors. We are thinking that temperature could make a difference, because when we're looking at this, what we sometimes call steam world, that all these terms are, yeah, someone came up with them, not all of them, all the researchers are using them. But for the hotter cases, it could be something like a steam world, because if you're having a planet that gets very hot, a lot of stuff evaporates, so a lot of the interior is evaporating, so it turns into steam. So we think it could be a steam world if it's hotter. It could be a water world if it's cooler. As I said before, water is also something lighter that we could fill in into this lower density. We can also have something that looks more like a gas world, where we have a lot of gas in the solid interior. So all of these three very different ideas are fitting the same mass and radius combination. So the same planet, and we can say, okay, all three combinations are possible. So this is very uncertain, and we don't know yet what to do with this. And then someone came up with the Haitian idea for the water world scenario, where Haitian is just a combination of a hydrogen-rich atmosphere and an ocean layer. And since with this we would have liquid water inside of a Sub-Neptune, people were like, ooh, could Sub-Neptunes be habitable? Could that be a thing? So there was a lot of discussion, and it's still very uncertain if this scenario could exist. But some modeling efforts say it could happen, others say it could not happen, it's very uncertain. But if it were a thing, it would mean that we could extend our search into the Sub-Neptune area to larger planets. When we're looking for biosignatures on such planets, they would be a little bit different. Because on Earth, we're having an atmosphere that is made out of nitrogen and oxygen. So we have what I showed in the beginning, those biosignatures of oxygen and methane together. But when we're looking at Sub-Neptunes, they have a different atmosphere. We're saying it's a hydrogen-rich atmosphere. So what we're hoping to find there, what we're looking for in the spectra, are other molecules, mainly those that are called dimethyl sulfide, dimethyl disulfide, so very complicated names, but just molecules that could hint for life, because on Earth they are made by marine phytoplankton and bacteria. But all these signatures, when we're finding them, they have to be interpreted in a planetary context. So just because you're finding these two molecules, it doesn't automatically mean, oh, there's life. Because you always have to consider, could other processes also make these molecules? Does it have to be life? So it always is very important to interpret this, of course, in the context. But if we're finding it, it is a nice, what it would be very interesting to know. But the reason for the Sub-Neptunes to be very popular now, and be a lot in the media also, because besides them being common, they also have other perks. When we're observing them, as I showed in the start, it's the same video again, we see that the larger planet gives us a larger dip in the brightness. And a larger dip means it's easier to detect. Because if you're having a lot of noise, we call it, so if there's a lot of other effects that are causing your data to wiggle around, you want to be sure that what you're seeing is actually a from a planet. And so a larger dip means larger certainty. Means it's easier to detect them. And then further, these objects have a hottier atmosphere, we say. So because their atmosphere is more extended, when you're having the light coming through, it gives a stronger, we say, fingerprint in that spectrum. So the molecules have more opportunity to absorb the light and you get a stronger signal often. So those are the perks. And with all of this, we are now coming to my current master project, where I'm taking a problem. So for one mass and radius combination, all these are possible. So we do need to look further there. We need to make more observations. We need to get more spectra. We need to understand more. Like here, we need to look into the planet's atmosphere to understand more. Because we can understand, as I said, the atmosphere composition better when we're taking a spectrum. But the main problem here is we cannot take spectra of every single planet. We have discovered quite a large Sub-Neptune population because they're so common. So how do we decide now which planets we're studying? We need to understand what they're made out of to understand if they could be habitable potentially. So how do we decide? Which one's first, which one's last, what do we do? And this is where the core idea from my master project is coming in. I called it a quantitative habitability framework. Sounds very complicated. Quantitative just means numerically assessing, so numbers. And habitability, the potential for habitability, not if they're really habitable, this is hard to understand. And framework just means I'm coding and programming. So I'm trying to make a prioritization tool, hard word, to understand which ones we should look into first. And this is the basic idea. I am taking observed data, so anything that we can actually see, because composition we cannot just look into the planet, that's not possible. But we can take something like the radius, we're getting that from transient measurements. We possibly can get a mass, that's from a different measurement. And then we can take the stellar properties from other measurements, and then we're taking all of this information that we have, and we're putting it through a code, to be honest. We're putting it through an analysis framework to try to understand what could be possible interiors in atmospheres. So what could potentially work with this combination of temperature, radius, mass, and the distance, etc. And then I'm trying to understand, could that planet be habitable? Could there be liquid water potentially possible? And how well is that planet actually to be observed? Because some planets are really tough to be observed. If they're very small in comparison to their star, it's very large to get any signal from there. So it's also important to understand, is it easy to observe them? Because then I'm going to put them high in the ranking. Or is it hard to observe them because they're getting further down? And in the end, from all of this I'm getting scores, and then they can be ranked, where you're saying, okay, the first one would be more interesting to look into than the last one. So to understand better what I mean here, we first take what we have, what I said, observed data, where we're getting the stellar properties, so from the star, we're getting everything that we have from the planet, every information that we get from our method where we found the planet. And based on what we have, we try to infer what we actually cannot see. So this is something that we do in astronomy often, that we infer something that we cannot directly see from what we have. It's a little complicated, but this is what we're doing here, because as I said, with the same mass and radius, we're getting different kinds of planets. So let's try to infer what they could potentially look like. Could it have thick hydrogen atmospheres? Is it thinner? Could it have more water-rich layers? Could it have no water-rich layers? All of that is what I'm trying to infer here. And then I am trying to assess the potential for habitability. So is it likely that there could be liquid water? Would that work for the planet? Could it have a suitable atmosphere? And then I'm also looking into how strong the signal we get there, and is it actually a good follow-up target, or will we have a hard time with it? And then lastly, I'm getting the ranking. So I'm going to prioritize the best follow-up targets, essentially. And I'm making the ranking. The first one is most promising. It is more likely to be habitable than the others. And also in combination too, it is probably better observable. We're getting strong signals from that one. And yeah, we're having very exciting times in front of us because what I'm trying to infer could maybe be better observed in the future. We're having nice telescopes and missions coming up. For example, we're having James Webb is already up, it's already doing a lot of work with analyzing atmospheres, for example. We're also having Ariel coming up from ESA in the future, which is also going to look into atmospheres. And of course, the topic of the talk, the F.Kaiser mission is coming up, which is going to find small planets, but probably also a ton of Sub-Neptunes because they are so common, so they might be a lot in the data. So now I'm already coming to my takeaway from this talk. So what I've been trying to say is just essentially, okay, we've all been looking for Earth-like planets. And this is very valid, this is totally reasonable because it's the example that we have. It's reasonable to search for Earth-like planets. But currently our missions are just not there yet. We're getting there probably very soon, I hope. To actually look into Earth-sized planets and find them better. But for now, maybe it's interesting to broaden our research and try to understand what are these sub-Neptunes made out of, and could some of them maybe be habitable? So maybe the search for life could be broader than just finding an Earth twin. Who knows? Thank you very much for your attention.